Hi, everyone. Today is April 15th, 2023. Thank you for joining the Silicon Valley Quantum Computing Group meetup. Today, we are talking about error correction, and this is for using mirror symmetries on D-Wave machines. I'm your host, Taposh Roy. If you have been with me for the last 5 or 6 sessions, you probably know this. I am a director at Kaiser Permanente of Innovation. I am focusing on digital twins, which includes optimization, simulation, modeling of long-term forecasting, like impacts of COVID in the 10 years down the line. Prior to that, I was a head of products for a couple of startups. I'm also the author of the book Medical Image Processing with Deep Learning. I'm writing a book on AI governance, which will be coming up in a month or so. With that, I'm going to go to the next slide, which is today's talk. So today we have a very, very interesting talk and a very interesting person joining us. Bhavika Bhanglamia is a PhD student. She's almost on the verge of graduating, and she's done some impressive work on error correction on quantum annealing with D-Wave computers. So we're going to have some fireside chat with her as well. And then we'll open up for the audience Q&A. Bhavika's talk is, as I said, is an error correction, but this is a summary of the session, right? She's going to talk about the quantum annealing machines, more specifically Adiabatic as opposed to the others. She's going to get us some detail. She's going to talk in a layman term so we all understand where it's coming from. But this is the overall essence of the talk. Okay, with that, I'm going to introduce Bhavika. Bhavika is a PhD in physics with a specialization in quantum computing from Mississippi State University. Her research work is truly multidisciplinary. She's been working on projects that include adiabatic, cold atom computing, gate-based modeling, and quantum algorithms in general. She has developed algorithms on a variety of hardware, including work with D-Wave, AIMS, NASA AIMS, and cold quanta. In this talk, she's going to introduce us to some of the work that she's been working on. Okay, with that, Bhavika, I'm going to stop sharing and I'm going to pass it on to you, and then you can take it from there. Okay.
Thank you, Taposh.
Okay.
Thank you, everyone, for joining. And uh, it is a great pleasure to represent my work to the Silicon Valley Quantum Computing Group, and very excited to share the work. So let me share my screen. So, uh, first of all, wish you all a belated, very happy World Quantum Day. So I may not get a chance to ask you questions. So starting with me asking you a question. So why we chose April 14th as a World Quantum Day? Anyone?
Well, I should not answer, but yeah, let's give
Yeah, I
everybody a
think,
chance.
What
yeah.
was the question? I didn't quite get it.
So yesterday was the World Quantum Day. Why we chose only April 14th as a World Quantum Day?
Oh, I have no idea.
So let me go ahead and answer these questions. So Planck constant is very important in the whole world of wave, because the quantum is related to wave, and the Planck constant is almost 4.13, and if you round figure that, it is 4.14. So 414, April 14 is known as the World Quantum Day. uh, so let's enter into the quantum world. So first of all, let me introduce my quantum computing group at Mississippi State University. As you can see, this is my advisor, Dr. Mark Watney. And we have other professors working in our group from electrical and computer science engineering, Dr. Sami Khan and Dr. Yaroslav Koshka. These two are the professors who are working with us. There are many postdoc students. Some of them are left, some of them are still associated with the projects which we are working on. Uh, there are some PhD students and some more students who are going to join the group. So main agenda of our group is to implement quantum algorithms to find new methods, technologies, and to promote the research groups, write the NSF grants and proposals to get access to the quantum devices. The main work is computational, so uh, we all do is get the hardware access and then implement the algorithm on quantum hardware rather than doing any experimental work. So I have been working on some of the areas, but these are what makes me more interested and towards the quantum computing field. So I started with superconducting qubits. So far, I also got a chance to use neutral atoms to work for my projects. My main projects are based on D-Wave, and my PhD project is based on the cold atom based quantum computer. We also developed some of the quantum machine learning techniques along with the ECE group at Mississippi State University. But my work is focusing on adiabatic quantum computing, which we will see how it works for D-Wave especially. Nowadays, gate model computing is a big boom in the uh, quantum computing field. And as we know that quantum computing field has, because the quantum computers are very sensitive, so it is required to protect the data. It is required to do not lose the information, and that's why many people are developing error mitigation and error correcting techniques to enhance the performance of quantum computers. There are some noise intermediate scale devices, quantum devices, which also I'm interested on, and I'm trying to explore more. So I joined the university in January 2017, and these are some of the projects which I have been working on since 5 to 6 years. I met my professor in December 2017, and at that time I did not know what exactly I'm going to do in my research work. But then once I started working, the first quantum computer or quantum computing device I got introduced to it was D-Wave. First project was spanning tree calculation, and in that we it was based on the random walk on quantum computer. And then following that, I uh, started working on another project. This is the quantum annealing error mitigation, where we find out the validity of the true ground states returned by any quantum annealer. Especially, we are using D-Wave quantum annealers. My third project was a coursework project in which we wanted to implement on the quantum computing device. This is a Wolf algorithm, and it is also the known as the cluster algorithm. So we developed a classical model where you can run the Monte Carlo using the cluster algorithm. Following after that, we started. I wanted to check that what happens when you do the quantum annealing on a classical computer. So we developed a code where we did the quantum annealing on a classical device. So there to run the one annealing, it takes 1 second on a classical computer, whereas if you run the same code on a quantum computer, it takes a very less time, which is in seconds. My next and main PhD project was ultra cold atoms, but I have explained these projects so many times, and that's why I wanted to choose something new to explain in this meeting. So rather than choosing the ultra cold atoms, I am choosing today to explain quantum annealing error mitigation method. But yeah, I would like to explain more in detail what is quantum annealing error mitigation method using mirror symmetries, what was the approach. And this project was funded by USRA, and we chose to use high performing performance computing collaboratory, which is situated in Starkville, which is a part of my university, Mississippi State University. And during using these supercomputers, we got a chance to access two devices. One was hosted at D-Wave, which was 2048 qubits, and one was hosted as NASA MS Research Center. So we used to access it remotely. So before we jump into the quantum world, I would like to go with a little bit overview what kind of qubit technologies are available nowadays, starting with superconducting qubits, in which most of the companies are using artificial quantum circuits to create 0 and 1 2 states. So this is what D-Wave is using so far, and they are using superconducting qubits made up of Josephson junctions. But there are other quantum computing technologies, qubit technologies are also available where they trap ion. So as you can see, there is a chip and then they are trapping the magnesium ions, and there are also some companies which are developing these kind of qubits experimentally. There is next is semiconducting qubits. As the name suggests, they take the semiconductor silicon as a material and they make the quantum dots and they make it as a qubit. So now here the word qubit meaning we are having the two states, and which is mostly 0 and 1. So from superposition state we are jumping to measuring the classical state 0 and 1. The next is topological qubit, and Microsoft is using topological qubits in that they use, instead of fermions and bosons, they used anions, which are quasi-particles, as a qubit. The next is cold atoms, which you can see that is a Albert device introduced by Cold Quanta Company, now known as Inflection. And why I know little bit more detail in this is because they are cooling down the atoms into the nanokelvin temperatures, and I have been using this device for my PhD project. Next is a photonic qubit. As you can see, they take the two photons and the angle entanglement, and they use it as a qubit. The next is NV centers in diamond, and the word NV meaning they take the diamond and then they replace the one atom with the nitrogen and create a valency beside it. So that is NV centers. So these are some of the technologies nowadays available, and maybe we can see different others more. Uh, Hoping to see the next 10 years will be the new technologies available. So my work is related to D-Wave, and D-Wave has a software environment where you can directly access the D-Wave quantum computers online using their solvers, which is known as Solver API, which they namely call as SAPI. And what we do is we use the classical computer and then we give the quantum machine instructions on a quantum computer. And here we are going to define the problem to the quantum computer and get the results from any quantum device. So this is the wave QPU, which you can see here, and they have cloud system also available, which they named as a D-Wave Leap, and they have a software development kit, which is known as Ocean SDK, where you can program the Hamiltonian, or you can say program the graph you want to embed in or the problem you want to implement on a quantum computer to get the result and to get the data. So first of all, how to formulate a problem on any quantum computer. So here on D-Wave, what we are focusing on is minimizing the objective function. So the objective function can have many local minimum, and it will have the one global minimum. So our main target is to formulate a problem in terms of objective function and then minimize the objective function in order to get the optimized solution. So here we are focusing on finding the global minimum, and it is having D wave is a very good in performing optimization problems so far. So there are a few types of optimization problems, and different optimization algorithms are also available. Few of them I'm keeping here, like based on the mathematical constraints and formulations, we can formulate the optimization problem and techniques. So some of them are like linear, non-linear, quadratic, some of them are integer and constraint, and some of them are continuous. So why I'm focusing more on optimization, because D-Wave has proven capability in optimizing a problem and finding the best solution for a given set of problems. So the main types of problems D-Wave is allowing a user to solve is quadratic models. So here you can see the quadratic models, the main three types of quadratic models are available on D-Wave. So you can formulate a problem either in binary quadratic model, which they name as BQM, then constraint quadratic model, which is CQM, and then discrete quadratic model is DQM. So mainly this project which I'm going to explain here, it is based on the binary quadratic model, and the binary quadratic model has further two types. You can formulate the problem in either Ising problem or a cube problem. So with these both we will also see in the coming slides. So first of all, constraint quadratic model, we will go with little bit overview for these. So this is the problem. So when you want to get the results from D-Wave, the first question comes is to formulate a problem. What kind of problem you want to solve on a D-Wave? So this is a CQM, constraint quadratic model, and we have the the form of equation, or we have the form of problem. So I will also explain that how did I converted my method into the quantum computer, the problem set, and then how I got data. So they can be constrained also, and these constraints are having number of inequalities and equalities respectively. So as the name suggests, this is constrained quadratic model. So first of all, we need to differentiate that what kind of problem we want to submit on a D-Wave. The next is a discrete quadratic model, and as the name suggests, it is made up of a polynomial discrete variables, and any problem or any energy, we can energy of a quantum system in so if we have any system and if you want to define the energy in quantum mechanics, this energy is considered as Hamiltonian. The name of the energy is considered as Hamiltonian. So you may hear this word a lot in my talk. So the discrete quadratic model is defined as h of d meaning having discrete variables, and C is again the constraint over here. But my work is mainly focused on BQM, and BQM is having the energy formula as you can see here, and these are the variables we are going to submit on a D-Wave. But binary quadratic model, it includes also quadratic unconstrained binary optimization, which is known as QPU. So starting with Ising model, we will also learn in little bit detail that what is Ising model, what Ising model represents. So here we see that there are two formulations, and when you use BQM, you can formulate the problem in either Ising or either in a Cubo, where Cubo does not include any constraint. So as you can see, the difference between Ising and Cubo, there is a spin -1 and +1. So why we are talking about the Ising model is it represents the spin system. So each qubit, when you give some magnetic field, in the end, it will give you the data in terms of spin up and spin down. So that will be spin up and down here we are getting, whereas if you are considering cubo, then the spin system is considered as either spin down, that is 0, and spin up, that is 1. So why we are focusing more on Ising model. So this little bit we are jumping on in a solid state physics where, as you can see that we have different neighbors with having a spin ups and down. It is randomly chosen, and then depending on when you introduce the magnetic field, the system will collapse into the classical spin, so that is known as spin up and spin down. So this is the best Ising spin model, and it represents any system which has spin up and down configuration. So on D wave they are using the Ising model, and that is why we are focusing more on. But here you can see there is the Hamiltonian, as Hamiltonian defines what is the energy of the system. Now, any quantum computer, what our target is to bring the qubits or the system into the ground state from any excited state. And the ground state is the global minimum, where what we discussed in objective function, that is where we are more interested in. So here it is Ising Hamiltonian, which represents how the adiabatic or how the annealing process works. So initially, this the initial Hamiltonian. That is what the energy of the system is in initial stages, and then we want to tell the quantum computer that okay, we are going to take two qubits, we are going to give +1 field to both of the qubits, and then we are going to entangle them. That is the entanglement strength, or you can say the coupling strength, is known as Jij over here. We took both of the qubit and now we want to give +1 ferromagnetic or antiferromagnetic field to it. So that is known as the local field on a quantum bit, that is known as Hi. And once we define the whole system, that is known as our final Hamiltonian. So what happens initially is the system is in initial Hamiltonian, then slowly we introduce the problem, that is final Hamiltonian, to the system, and in the end the system gives us the global solution of for the problem which we define to the D-wave quantum computer. So yeah, it will be little bit more into the quantum uh, annealing thing. So for these we need to understand that how to connect the qubits, and what exactly the qubits are. So here you can see this is the unit cell. The smallest unit, the smallest part of the quantum computer is known as the unit cell here. And you can see here, this is the Chimera topology. So there are different topologies available right now. Pegasus, there is another topology available, but I started my work with the Chimera. And then in this part is known as the unit cell, where you have the nodes. So each node has a number, and you can give the local field on, or a magnetic field on a qubit. So what happens when you give a field to a qubit, and when it interacts with the another qubit's field, the probability of getting the global global minimum, it changes depending on what kind of graphs you are embedding. So these kind of you can compare with restricted Boltzmann machine kind of architecture. And we started our work on the Chimera graph. This is also known as K44 technology, having 4 nominal length, and then each qubit is connected to 6 different other qubits. So first and foremost, when I started my work, what happens in quantum adiabatic annealing, and what does this adiabatic word mean? So any system will win. What our target is to bring the system from higher energy to the ground energy and find out the ground state. So that ground state is known as the lowest energy or the minimum energy. So here initially the qubit will be in a superposition state of 0 and 1. But as the system evolves, the probability of getting 0 and 1 when there is no magnetic field, it can either fall in 0 or it can fall in 1. So the 0 and 1 is known as the classical state. But when you apply the magnetic field on any qubit, then we are introducing some field to the qubit, and we are finding the higher probability of getting the lower energy state. And in the end, we are finding the lowest energy state, which is known as global minimum. But then the whole process is known as quantum annealing process. So starting from the higher energy or the superposition state, and we are getting the lowest energy, this is the annealing process. But then the question is, why do we call it adiabatic? So as we saw in the previous slides, there is initial Hamiltonian and on the D wave, and then we are introducing problem Hamiltonian to the D wave. Now, when you introduce this problem Hamiltonian to the D wave, it means you are disturbing the system, and in that case, it should be very slow process where the system does not jump from the lower energy gap to the higher energy gap. So we want to maintain the lower energy state all the time, and this process should be very, very slow. Um, in like microseconds. So that's why we are calling it adiabatic. So in adiabatic process, the initial and final state, they don't have too much change, or are almost same. But there is another approximation in quantum mechanics known as sudden approximation, where the initial state and final states are two different things. Now what we are going to do is, we want to find out is what is the problem Hamiltonian we want to submit on D wave. So that was my first question, that what is the problem Hamiltonian. So as you can see, it is made up of two things. It is of local fields on a quantum bit, and when you entangle two bits, then what will be the coupling strength. So this was the method. As this, we know that this is the initial Hamiltonian, the initial energy. So word Hamiltonian, when I speak all the time, you can consider is the energy. So initially the energy of the system was this, and then we are defining the problem Hamiltonian. But now my problem Hamiltonian is made up of three different parts. One is the problem, next is the mirror of the problem, and now I want to connect both of the parts with the coupling strength, that is the coupling Hamiltonian. So what happens is, this, since A of t and B of t um, both of our uh, the function of time, and this is time dependent process. So even in quantum computing, we have some of the time dependent Hamiltonian and time independent Hamiltonian. Okay, so what is the method we want to try? First, I have the initial Hamiltonian, I want to submit the problem, and then for my given problem, what will be the optimal solution I should get. But any quantum annealer on D wave does not guarantee you that whatever ground state or the solutions you have found is the true ground state. And that is what we are mainly focusing in, that um, what is the validity of the ground state written by the um, D-wave annealer. So that is what we are trying to do. So we are mitigating the error. So as you can see, this is the whole method. And why we are calling it mirror symmetry is because you have here um, four rows and two columns. So we are dividing the whole chimera into the two parts first. So as you can see, the left side part is all the qubits are green colored, and right side part is the orange color qubits. And then we are defining the mirror axis. There is no physical axis over there, but just we are imagining that both of the part are connected with the ferromagnetic or antiferromagnetic field. Now, when you give, when you take two qubits, if you have both of the qubits with local fields on them 0, and when you connect both of them with the ferromagnetic field, you submit this problem. By meaning of ferromagnetic field is the strength. Strength can be +1, -1, or any magnitude. So when you submit this problem on D wave, in the end, the system will collapse, and it will give you both either spin up or spin down, depending on how did you connect. So if I connected with ferromagnetic spin, then both of them in the end will give you spin up. or spin down, same spin. But if I take the antiferromagnetic field, then in the end, one qubit will have spin up, another will have spin down, or vice versa. So this is how we are focusing more on that. If you have two qubits and if you connect them like this, why not to try having two exact graphs, like having, let's say, 2000 qubit on left side, 2000 qubit on right side, implementing the same kind of graph. So here, or whatever coupling strength is here, it has its mirror over here. So in the first part, we divided the whole chimera, decided how many qubits will be on the left part and right side. Second thing is we introduced the problem Hamiltonian. Problem Hamiltonian meaning you take the qubit, another qubit, and decide what is the connection strength is, what is the coupling strength is. So we took that part, we mirrored the whole graph into the next the another part, and then now we these both are like having the same coupling strength, same problem Hamiltonian. Now we both combined with the coupling strength HC, that was the coupling Hamiltonian. So the main agenda here is, if in the end we give 1000 anneal or number of anneals, if we get one solution which reflects the mirror symmetry, spin symmetry, like let's say if this qubit has plus one, then if this qubit has also plus one, similarly if this has minus one, this has minus one, then we claim that this state is ground state, or actual true ground state received by the d wave quantum annealer. So this was the whole method to find out or to mitigate the error on quantum d waves, different generations of quantum annealers. So these we implemented on different qubits, with 1000, started with 1000, some of them were 2000, and then one was at NASA, and then currently we are implementing on 5000 qubit machine. These are the results. These are saying that out of 1000 annealing, so uh, the one annealing process defines as, you have the Hamiltonian, you implement the problem Hamiltonian to the system, and you find out the solution. That is called one annealing process. Out of 1000, how many solutions we got was having mirror spin symmetry in the end. So this is known as p symmetric. So we got the p symmetric, and this is the data for different DWP and DWC. Here, we need to make sure that if the left part is missing any qubits or coupler, then you have to remove the same qubit and coupler, or its mirror qubit and coupler from the another part, because both of them should look exactly like same. That's why we call it mirror symmetry. And for these, we had two things to choose. First was first was to introduce the local fields. So there are some of them which are having no local fields on quantum bits, and there are coupling strength which were chosen from the sedan set, which is the sedan set is defined over here. Then we compared the performances of two different quantum annealers, which are named here. And here we have changed these number of rows. So number of row is, the one row has 16 unit cell, and that way we chose 16 all other number of rows having different unit cells. So as we can see that DWC NASA, so having with local fields, we are getting the higher probability of getting symmetric solutions with the column index. So now this column index is, if you go here, so these, the whole, this is like 4 by 4, 4 rows and 4 rows and 4 columns. When we say n is equal to 1, we are just considering and taking only this part of the chimera, that is n is equal to 1. And then when you consider these two, that is n is equal to 2. So we slowly increase the size of the graph, and we saw how probability of getting symmetric solution changes. Now, the main challenge was to compare the performances of different generation of quantum annealers. That was our second task. So first we found out the validity of solution. So if you get the p symmetric very higher, it means you are getting a very nice symmetric solutions, or the probability of getting symmetric solution is very nice. So next was, uh, after checking the validity, the next target was to compare the performances. As you can see, we started calculating the Hamming distance for different uh, the same implemented graph. We started calculating the Hamming distance, and based on that, we came to know that from previous generations of quantum annealers, D-Wave's current quantum annealers are performing better. So why these method is important? So it does not require the prior knowledge of the true ground state. So when you submit any problem to the quantum D-Wave annealer, you don't need to know that whether this should be the ground state, or another should be the ground state. It just, you have to take the mirror symmetry, implement on a graph, and it will give you the exact ground state. That is what we are claiming for. Next is these Chimera topology is known as K44 technology, where 4 is the nominal length. So instead of K44, you can also work with another topology. And the only thing is, you should be able to divide the whole graph into two parts, mirror them exactly, should have the equal number of qubits and couplers, and then you can connect it with the ferromagnetic strength. These method is also extended to hypergraph, so where more than two body interactions are present, and that we we hope we'll be working on very soon. And this can be used on arbitrary to local Hamiltonians and shown as to QMI complexity class. So the whole summary of the method is two things. We found out the validity of ground states returned by different generation of quantum annealers, and second is we compared the performance of different quantum annealers. So this is the current project I am working on. And as you can see, this is the Pegasus graph. So when you can, if you can zoom that, you will see that the Pegasus is the current topology of D-Wave quantum annealer, where it is made up of 5,670 qubits, and these all uh, this is very complicated than the Chimera topology. So what I am doing is I'm implementing the Chimera connections on the Pegasus. So I'm connecting them with the local fields and coupling strengths to implement my method or extend the method on Pegasus. Next will be, so as I said, this is a K88. So other than K44, you can also use this method on K88 technology. And the upcoming is Zephyr tech topology, and then that is going to be very complicated. So my current work is based on Pegasus topology, and we are implementing this method to find out that Pegasus Pegasus performing better than Chimera. So there are some references I have used, and thank you.
Bhavika, this is phenomenal. So thank you for sharing all the awesome work. First question that I have, I know,
Hmm.
and I mean, we were thinking we are still in the NISQ area, which is up to
Hmm.
100 qubits, and this is
Mm.
groundbreaking. You're talking about thousands of qubits, 5,000 qubits. Do you think we are beyond the NISQ area right now?
So I think we can be. So the short answer, we can be. So we cannot say that, yeah, exactly, but yeah, I think we
Okay,
can be.
so that leads to my the next question, which is, what are the advantages of this, of say maybe D-Wave,
Mm-hmm.
on the classical optimization? So there are classical optimization tools.
Mm-hmm.
Gurobi is there. There is IBM has a product
Mm-hmm.
as well. Um, so can you tell us a few advantages why we should use quantum optimizer as opposed to a classical one?
Yeah, so classical optimization is very useful as well, but then there are some problems which are known as NP complete problem, which cannot be completed in polynomial time, where classical computers have limitations, and that is the reason where we choose to use quantum computers for optimization rather than classical computers.
Mhm. Okay.
Mm-hmm.
So basically you're saying that, okay, problems that are NP complete, let's use
Mm-hmm.
them as opposed to the
Yeah,
other problems which are easily solved. That's
right.
good. And when you solve talking about problems, before I open up to the audience, one question for you is, what are the some of the example problems that can be solved today with a quantum computer?
So if the recent study, if you might have observed, Volkswagen, they solved traffic optimization problem using D-Wave. So
Mhm.
that is what more interested is, that you can also use D-Wave in real world uh, problems, like you can solve finance problems as well. So that is what I'm looking forward to it, but there are few in banking, finance, and one of them is in traffic optimization. So
Got it, got it, got it. I certainly want to open up the forum platform here for the audience to ask a few questions. So anybody has questions for Bhavika based on the talk that we have heard?
I have actually. Can I speak or should I
Sure,
type
please
it
go
in?
ahead. Go
yeah,
ahead.
yeah, please go ahead.
Okay, so uh, we have a problem Hamiltonian. It seems that we have to submit it to the machine,
Mm-hmm.
right? And then, but the thing is that the initial Hamiltonian, is it set by default, or can we also modify the initial Hamiltonian? I mean, I think it's
No.
of the sigma x. Can we
Yeah,
modify those, or it's set already?
so it is set already for it's a transverse field with polymetrics sigma x, so it is already defined to the D wave. And then you define, the only thing you define to the D wave is your problem Hamiltonian, which contains the local fields and the coupling strength. But let's say you want to have another problem, you are not interested in embedding a graph, you are interested in a diet plan, that okay, I'm going to the gym, and then my protein should be this, my fat should be intake should be this, carbohydrate should be this. So you want to optimize that. If you have the 1,000 diet plan, what is the best diet plan you can have to get the good result? So you can also formulate this problem, and it is known as CQM. So in all the processes, the only thing you are defining is the problem Hamiltonian.
Okay, thank you.
Mhm.
Thank
On that, right, does D-Wave provide any specific capabilities for CQM, Bhavika?
uh so far it depends on, like uh, we don't know whether the ground state is true state or not, but I think it performs way better. So it's a way more capable than classical, I believe. Uh, but yeah, CQM are mainly concerned or mainly formulated in terms where you are not considering the spin model. You are considering the, when you play with the data, we are using the CQM rather than having spin model or the magnetic or pyramids kind of graph embedding thing. So these are kind of two things. Yeah.
Got it, got it.
Hmm.
Any other questions from the audience?
Yes.
Go ahead, Supreet.
Hi, Bhavika.
Hi.
Wonderful talk. I couldn't
Thank you.
attend right from the beginning, but I attended most part of it. So my question is, you mentioned Volkswagen solving the D-Wave problem. So
Yeah.
so even I have been working in a company. Have
Hmm.
been working
Oh
on
wow.
D-Wave machine. Um,
Hmm.
so the thing is that we are usually dealing with large scale problems.
Hmm.
uh, D-Wave D-Wave doesn't really run everything on the quantum annealer. It runs. We have to choose the leap hybrid solver,
Right.
right?
Right. Right.
And we have no control over which part is actually run on the quantum computer. But for that, we have some other hybrid algorithms I know that,
Mm.
but see, since we do not have any control over that, so like how do we know? I mean, this is very tricky. How does D-Wave choose which one to run on the quantum annealer, and how do we know whether it actually is giving us advantage?
Yes.
What?
Yeah, I think I are you talking about choosing a solver?
No, not choosing a solver. So
Mm.
D-Wave runs some part of the Hamiltonian problem
Mm.
Hamiltonian on the quantum
Yeah.
annealer, right? It has some QPU
Yeah.
time, and then it has most of it is
Yeah.
run with proper, classical algorithms, right? So
Yeah.
how does D-Wave choose that? It's a complete black box from what I know. We do
Yeah.
not know what exactly D-Wave does, but to choose some part of the problem to be run on the quantum array.
Right. So, what my point of view for that is, they have default settings. So definitely, when there are few default settings, you cannot play with that too deeply. But there are few things which you can control, having like types of solvers, number of qubits, the coupling ranges, and there are even default settings. I think the annealing time and all, you can choose it, but how or what part of it is choosing that, other than qubits, local fields and couplers, I don't think we can select the other parts so far, what I have chosen. Yeah.
Okay. Thank you,
Mhm,
Bhavika.
mhm. Thank you, Supreet.
Thank you. I have one other question which I've been dying to ask, right? So
Mm-hmm.
if you use IBM or any other thing, you are on the gate
Mm.
model, right?
Yeah.
Now, can you give us some insights into, are the gate models applicable on D-Wave, or what is D-Wave's perspective there?
So yeah, I was bugging D-Wave people, D-Wave support people, for because I'm too much interested in seeing that how these large system uh, can be useful for the gate model computing, because that is the 95% of world is working on at the moment. But what their answer was is they are still working on implementing that. You can have some simulators, you can just run code on that, but there is no proper quantum processing unit for available for the gate model computing so far. So yeah, I think oppo- annealing is an opposed approach to the gate model. uh, and then that will be very interesting and very nice that to see that how you can use 5670 qubits for gate model computing. Yeah, but I
Yeah,
still they are working. Yeah.
yeah. And I take it back when I talk
Hmm.
about the NISQ area and stuff like that. NISQ is based on the fundamental thinking of the gate model, as
Mm.
opposed to the
Yeah.
annealing
Mm.
approach that
Mm.
they went ahead with. Yeah.
Mm.
Any other questions from the audience? Because otherwise I keep on asking. Okay.
Yeah, I have one more thing to ask.
Please go ahead, Abhiyan.
Okay, so so I mean, what I get is that D-Wave is creating a kind of cost function, and its advantage is to reach global minima by
Mm.
tunneling over local minimas or like that,
Mhm.
rather than travel classically over the mountain barrier. It's tunneling. Is that the advantage, right?
Yes, yes, that's right. That's exactly right.
Okay, and so only can binary type of variables like you have shown that in Ising
Mm.
model of cuboformism we have only binary values for the variables,
Right. So
minus one.
mm, yeah. So it
So,
depends on what kind of problem you are solving. So binary variables, they are considered in BQM. So remaining, but yeah, most of the time it works with the BQM. Yeah.
so uh, can the continuous variables be transformed to be solved?
I so when we talk about continuous variable, we can talk about the functions rather than having just variables. So that's what I'm understanding. So far, I haven't got any chance to play with that, or uh, we have just played with the discrete variables, you can say, or the binary one, and that is what more they are focusing on. So I doubt we have any continuous variable implementation you can run with the D-Wave.
Okay, thank you.
Mm-hmm.
Thank you so
Mm-hmm.
On that, right, I just want to double down on, you talked about within the binary, you talked about
Mm-hmm.
Ising as well as the cube
Mm-hmm.
approach, right?
Mm-hmm.
Can you give us why are we more interested in the Ising class, or why are we interested at all in the Ising spin class?
Right. So the whole spin structure is based on Ising spin model, which is focusing on spin glass. And spin glass has property of like it gives you the optimal solution in frustration. So there are many more properties of the spin glass, but why we are focusing on that is because it's giving you the solutions in terms of spins, and that is why mm, um, the Ernst Ising,
Mhm.
he was the one who introduced the Ising model, and that is why we are considering it to get the spin solutions. And
Mhm.
when you want to compare the quantum with the solid state model, we are taking two-dimensional Ising spin model in order to explain our problem and implement or analyze the solutions in terms of spin. So yeah, in short, the whenever you talk about a spin model, we can
Mhm.
talk about the Ising spin model is the best representation.
Got it, got it, got it.
Hmm.
Any questions from the audience? Okay, maybe one last question on your main topic, error mitigation, right?
Yeah. Hmm.
Um, can you tell us a few more things about given your method, are
Hmm.
there, what is the error rate? Is it possible to fix the errors? Where do you see this going as well?
So when we talk about gate models, we talk about fidelity and everything, right?
Mhm.
How accurate our results are. But in this case, um, it just finds the validity of the true ground state. So the whole concept is when you connect two qubits with ferromagnetic strength, both
Mhm.
should be either up, both should be either down. That's the quantum mechanics fundamental. But then here, we are not talking about only two qubits. We are talking about the whole graph of like maybe 2000 qubits left, same graph, 2000 qubits, right? And then we are trying to implement this. So it finds the validity in terms of that, okay, if you find the symmetric spin, each qubit and its mirror has the same spin, you found the true ground state. That is, we are claiming 100% will be the ground state, because it cannot be possible. That is that is the base of the spin model and the magnetic field. So if you get the symmetric spin
Mhm.
for a given strength,
Mhm.
then it is the true ground state we are claiming.
Mhm.
I
Yeah,
think I answered your
no, I think you did. I mean,
okay.
it's not black and white. Given in the quantum field anytime. Thank you for that. I think
Mm,
Bill has a very good question. Bill, do you want
mm.
to ask your question or you want me to read it?
Yeah, I think we should read in
Let
chat.
me read
There
it.
are five chats. Right?
Hi,
Yeah,
can you hear me?
yeah, Bill, we can hear you.
Yeah.
Hi. So the testing that you've done, have you done this with the hybrid CQM or the hybrid DQM
So
samplers?
this is a graph embedding method. As we discussed, when you have the lot of data, let's say traffic optimization, or you want to play with some of the diet plan or 3D bin packing problems, then we can consider about CQM, where you have constraints. But my problem does not include any constraint, and so we chose to use BQM, and it fits very nicely on Ising model. So far, I haven't used CQM for my project, but I chose to use BQM based on what kind of problem I want to implement on a D-Wave.
Okay, thanks. The reason why I ask is when we've compared
Mm,
hybrid CQM results to classical. Sometimes we've gotten some mixed results, and
yeah.
I was wondering.
Wow. That's nice. Yeah. I think D-Wave optimizers are maybe very nice or better than the classical optimizer. That's what I'm claiming for specific problems. Yeah, need to be. Okay.
Okay, thanks so much.
Yeah, that's an excellent question. I know we have 5 minutes remaining. If there are any questions, audience, please, this is an opportunity to ask Bhavika, or otherwise we can give now 4 minutes back, yeah, to everyone. Okay, I don't hear any questions, Bhavika. Thank you for being part of this discussion.
Bhavika, I have
Oh,
a
go
question.
ahead.
Suppose I have a question. So,
Please go ahead.
uh,
Yes.
I'm sorry, I'm asking this question because I couldn't attend the talk right from the beginning.
Yeah,
I
yeah, yeah,
hope
no
this
problem.
Go ahead, please.
recording is going to be shared. Second, so the whole point of, from what I understand, the whole point of this paper is, it finally it gives us a validity to say that, okay, we have actually gotten the ground state. That's the
Right,
whole
right.
point of the paper, right?
Mm-hmm.
Okay. So usually we do not have a way of verifying the solution. We do not really have a way of saying this is actually the ground state. But now, since you see two solutions, and we have connected with the ferromagnetic connection coupling,
Mm-hmm.
so we are actually able to verify that we actually have the ground state, right? That's the point.
Yes, that is first thing, and then second we compared the performances. So
Okay.
let's say you have the 2000. They have first started with the, I think, 512 qubits. Then they gave 2048 qubits. Now 5000. So out of even 2048, they are having different chips. They are different QPUs. So which one performs? They are having lower noise. So which one performs better? So that is what we are also um, implementing by calculating Hamming distance. So far we are think like our method says that the performance of current generation of quantum computer is better than the previous one. So right now we are implementing on Pegasus, and we want to compare that is Pegasus better than the previous Chimera topology or the other old generations of quantum annealer. So that is another thing also we are right trying to verify.
Thank you,
Thank you.
Bhavika.
Thank you very much.
Thank you, Supreet. Thank you. Questions are always good.
Yeah, I'm getting very nice, interesting questions, and yeah, it's good. Thank you for.
So I think the question from Bill was, will this recording will be available? Yeah, the recording will be available. And then there was another question that will the slides will be available, Bhavika. Are you okay to share the slides as well?
Yeah, okay. That is
Okay, so
fine. It's completely.
I will provide the link to the slides. They will be all
Mhm.
posted in the YouTube channel for the Silicon Valley
Oh,
Quantum
wow.
Computing Group.
Okay. Okay.
So thank you, everyone. Thank you for spending your Saturday morning for people in the West Coast like me, and thank you, Bhavika, for your lunchtime or noon time for people in the West Coast and everywhere across the world. Thank you, everyone, and have
Thank
a
you
good
for
rest of the weekend.
yeah.
Yeah,
Thank you for joining me, and it was very nice experience. Thank you, Taposh, for giving me an opportunity to present my work, and it's a very interesting talks and everything. And on top of that, I got very interesting questions. So yeah, thank you so much, all of you, for joining.
thank you, thank you. Have a good weekend, everybody. Bye.
Bye.